I'm Hudama, and this is my final project video for ENPM 701 Autonomous Robotics. Over the course of the semester, I designed, built, and programmed an autonomous robot from scratch using the principles we learned in class. The course was structured into 5 distinct modules: perception, locomotion and kinematics, localization with sensors such as cameras, IMUs, ultrasonic sensors, as well as planning and navigation, and Internet of Things, which we used in order to communicate with our robots remotely through email actually. This entire project was inspired by Mars rover missions where we don't have access to the robots in the case of being a whole other planet. And we need to build robots and systems and software that's reliable and robust enough to trust when we are put in situations where we have no access to the environment or the robot. The final goal of this project or this course was called the Grand Challenge, where the robot is placed in an arena with 9 blocks in a cluttered environment, and the robot must go and retrieve 3 red, 3 green, and 3 blue blocks in that order. So 9 blocks in total, and it must go and retrieve those blocks without dropping the blocks, making sure that they are placed within a construction zone, and also making sure that you don't run into the walls in the environment as well. So the challenge sounds easy enough, right? So we all thought, and we will go over the hurdles that we faced in developing the robot, but for now let's just roll over a montage of building the robot throughout the semester. Just an overview of how the robot was built and the progression that we followed. The first couple of weeks were spent building the robot kit itself that came just as parts as the metal frame and the motors, the encoders, as well as learning a little bit more about the Raspberry Pi every single day. So one of our first projects was to get the Raspberry Pi camera connected and being able to record a video or take a picture with that, which is key to our success in this challenge. We built the robot frame painstakingly in some cases, as we had smaller bolts and nuts that needed to be screwed on that kept falling, and you need a high level of dexterity in some cases to make sure that everything is going in as it's supposed to. Another thing that we did in the following weeks was connect the ultrasonic sensor, which the professor warned us is something that we need to do carefully, otherwise we might be able to short the entire Raspberry Pi 4B. So we did that, ensuring that we built a voltage divider between the Raspberry Pi as well as the ultrasonic sensor, as we do not want to short the circuit and short the Raspberry Pi, as that's a lot of money down the drain and a lot of progress lost as well. So that's something we had to do, and another thing that we did eventually was integrate the IMU. So the IMU interfaces with the Raspberry Pi using a serial connection, and we use an Arduino Nano, which is connected to a BNU 095 IMU sensor, and we extract the yaw and the orientation of the robot for localization and navigation purposes. We also built the gripper from scratch by assembling all the different parts of the gripper, maintaining, so you can't tighten everything. It has to have a little bit of slack to it so that the parts can actually move, and then we tie it down to a servo, which is used, and we control the servo by assigning it a duty cycle, a PWM duty cycle. In my case, it was between 4 and 8, and that is the open and closed positions respectively. In terms of perception, we had 2 main challenges, as the Grand Challenge required us to, 1, segregate each block into 3 different colors, red, green, blue, and deliver those in a particular order. We did this through HSV masking and defining upper and lower ranges for that color value. And this enabled us to mask out the region and see only the color we wanted when it came to perception. And so that's the only thing the robot saw during that part of the program. The second thing that we needed to do that was significantly more challenging was estimate the distance away from the block. And these blocks are shaped in such a way that the aspect ratio changes as well as you move further away from the camera, especially if you cut them off a little bit. And the way that we achieved the distance estimation, as we don't have any long range sensors such as LiDAR or time of flight, is we took approximate bounding box measurements for each block depending on how far away it was from the camera. So if the block is about this far away from the camera, say this is about maybe around a meter, say about a meter away, it's going to have a certain bounding box size defined in terms of the width and height of the rectangle that's surrounding it. But if I move it further back, the rectangle that's surrounding it is going to get smaller and smaller. And we can track the position of this at different distance intervals, and we will be able to create a somewhat approximate map of how far the block is from the camera. Along with the encoders, we wanted to track the angular heading of the robot as well, so we can reliably keep making sure that we can continue doing the same path over and over again, such as turning 90 degrees and forming a rectangle, for example, a rectangular path, which is something that we did for one of our assignments. So for this, we use an IMU, inertial measurement unit, and this sensor actually has a lot of sensors on board. It's a 9-axis sensor, and this can measure roll, pitch, yaw, as well as other orientations. And we only use the yaw values in our case, since our robot is we don't expect it to flip around in any other way. So we only use the yaw values in this case. And we use this to track where the robot is going and where the robot is coming from. So in my case, I used this in the Grand Challenge to ensure that the robot knew where it started from, and knew where it is gone to. And it was able to calculate a straight line path back to the start point, so that once it retrieves the block, it is able to go back to the start point and drop the block right there. So my strategy for the Grand Challenge was to first drive towards the construction zone from the landing zone itself, and use the construction zone as the start point for the robot. And my strategy was, after that, was search for the block. So if the block is not in the field of view itself, it will go through a search pattern where it starts turning right and then left, and then again starts turning more right and more left until it finds the block. And then once the block is identified of the color that it's looking for at the time, it will then center itself with that bounding box that's being formed, and then the robot will move in increments of 20 centimeters, correcting its heading every time. So some of the hurdles that we had to cross over in trying to get the robot ready for the Grand Challenge was, one, being able to reliably grip the blocks. If the block wasn't between and it was not going for that, it would knock it over. And considering the shape of the block, if it hits it on the top, if it hits it closer to the top, it's just going to knock it over. Another issue that was one way the blocks are toppled over. And the other issue I had was, after it tried to grip it, it would then topple over within the gripper itself, and the gripper would lose grip of it as well, and so the robot would return empty-handed to the construction zone. This happened for a reason I understood later, as the flow that was there in the Grand Challenge arena was very rough at the end of 2 runs, which my best score was 6 out of 9 blocks. Overall, I'm really happy after this course. This course made me learn a lot. I'm really proud of what I achieved in this semester, and I hope to build more projects like this. Thank you.